Welcome to this coding problem walkthrough. Today, we'll explore LeetCode problem number 1113, titled Not Available. While the exact details of the problem are unclear, we'll outline a general framework to approach and solve similar types of coding challenges. Let's dive in and learn together. It appears that the details for LeetCode problem number 1113, titled Not Available, are not accessible or have not been provided in this prompt. Without the actual problem statement, constraints, or examples, I cannot generate a comprehensive description. Please clarify or provide additional context if available. Thank you. When approaching any coding problem, it's important to have a structured framework. This allows us to tackle a variety of challenges, whether the problem involves array manipulation, dynamic programming, graph traversal, or string processing. The first method to consider is the brute force approach. This is often the most intuitive way to solve a problem because it directly implements the requirements step by step without focusing on optimization. While it's a great way to ensure correctness, brute force solutions typically involve iterating over all possible combinations or permutations, which can result in higher time complexities, such as O, n squared, or worse. This makes them less efficient for larger input sizes. On the other hand, optimized approaches aim to reduce unnecessary computations by leveraging specific insights about the problem. These might include techniques like using hash maps for constant time lookups, sorting to simplify comparisons, binary search for ordered data, or sliding windows to efficiently handle subarray problems. These strategies help improve performance, making the solutions more practical for larger datasets. Optimization, however, is not just about faster solutions. It's also about recognizing patterns and constraints in the problem. For instance, if the task involves finding a subarray or a subset that meets certain criteria, techniques like sliding windows or dynamic programming can be particularly effective. These methods exploit the structure of the data to avoid redundant work. The trade-off here is that optimized solutions, while efficient, can be more complex to develop and debug. Another set of techniques to consider includes divide and conquer and greedy algorithms. Divide and conquer is especially useful for problems where the solution can be broken into smaller, more manageable parts, such as in merge sort or quicksort. Greedy algorithms, on the other hand, focus on making the best local decision at each step, which can lead to a globally optimal solution in certain problem types. However, these approaches come with their own limitations. Greedy methods might not work well if the problem has edge cases where local choices lead to suboptimal results, while divide and conquer can sometimes use excessive memory due to recursion. The choice of strategy ultimately depends on the problem's details, including the type of data, the constraints provided, and the overall context. For example, if the problem involves searching or sorting within a dataset, algorithms like binary search or quicksort are strong candidates. If it revolves around finding subsets or sequences, dynamic programming is often the go-to approach. For graph-based problems, techniques such as breadth-first search, depth-first search, or Dijkstra's algorithm are typically effective. The process of selecting a strategy often begins with implementing a brute force solution to validate correctness. Once that's achieved, optimization techniques can be applied to improve efficiency. Alternatives like divide and conquer or greedy methods are considered when the problem structure aligns with their strengths. Ultimately, the chosen strategy is about striking a balance between correctness, performance, and clarity in the implementation, ensuring that the solution is both effective and maintainable. To begin solving any algorithmic problem, it's essential to first understand the problem statement thoroughly. This means carefully reading the requirements, identifying the expected inputs, outputs, constraints, and potential edge cases. For instance, if the problem deals with arrays, you should ask questions like, what is the size of the array? Are there any specific properties, such as whether the array is sorted? Similarly, you need to consider constraints like time or space complexity limits, and account for edge cases such as empty arrays, single-element arrays, or arrays with duplicate elements. Once you have a clear understanding of the problem, the next step is to identify an approach. Depending on the type of problem, you can select a suitable algorithmic strategy. For searching or sorting problems, techniques like binary search, two-pointer methods, or divide and conquer algorithms might be appropriate. For optimization problems, dynamic programming or greedy approaches can be considered, while graph-based problems often rely on traversal techniques like BFS, DFS, or algorithms like Dijkstra's. A good practice is to start with a brute force solution to establish a baseline understanding before focusing on optimization. Following this, the algorithm is designed by breaking it into smaller, more manageable steps. This typically starts with input parsing, where the raw input is read and transformed into a format that's easier to work with, such as arrays or hash maps. After parsing the input, the next step is to implement the core logic of the algorithm. This involves writing the main operations, such as looping through data structures, evaluating conditions, or performing necessary calculations to solve the problem. Once the core logic is in place, the output must be constructed in the format specified by the problem requirements, such as a list, string, or any other expected structure. With the algorithm designed, it's important to then focus on optimizing the solution. This means carefully analyzing the time and space complexity of your implementation to identify potential bottlenecks. Using efficient data structures can significantly improve performance. For example, hash maps allow quick lookups, heaps or priority queues are useful for dynamic minimum or maximum operations, and stacks or queues can simplify sequential processing tasks. Additionally, you can optimize loops and recursive calls to eliminate unnecessary computations. Finally, the algorithm is translated into code. For instance, in Python, you would break the problem into steps such as parsing the input, applying the core logic, and constructing the output. This structured approach ensures clarity and logical flow in the implementation. Once the code is implemented, the next critical step is testing. This involves running your solution against a variety of test cases to ensure correctness and robustness. These test cases can include normal cases that fall within the problem's constraints, edge cases like the smallest or largest possible inputs, and stress tests with large inputs to evaluate performance under extreme conditions. Testing helps uncover potential flaws or inefficiencies in your implementation. Key insights can also guide your approach to problem solving. For example, divide and conquer algorithms simplify problems by breaking them into smaller subproblems, as seen in merge sort. Greedy strategies work well in scenarios where making the best local choice leads to the optimal global solution, such as interval scheduling. Additionally, it's important to consider space-time trade-offs. Using extra memory, such as hash maps, can reduce computational time, which might be essential for meeting performance constraints. The choice of data structures also plays a significant role. Arrays are great for sequential data and efficient indexed access, hash maps allow constant average time complexity for lookups and updates, and heaps are ideal for maintaining dynamic order statistics like finding medians in real time. Graphs are another powerful data structure, particularly useful for representing relationships between entities. Common representations include adjacency lists for space efficiency and adjacency matrices for quick edge lookups. When solving problems, edge cases must always be considered. For example, algorithms should handle scenarios like empty or null inputs, boundary values at the extremes of constraints, and unexpected or malformed data, depending on the problem requirements. Testing these edge cases ensures the solution is robust and reliable. Concrete examples of test cases can help illustrate this process. For instance, given an input like 1, 2, 3, the expected output would be a processed result based on the algorithm's logic. For an empty input, the result might simply be an empty output. Similarly, inputs with a mix of values, such as 1000, -1000, 0, should be processed correctly to produce the desired output. Lastly, complexity analysis is key to understanding the efficiency of your solution. Time complexity measures the number of operations relative to the input size, such as O, n squared, for nested loops over n elements. Space complexity evaluates the additional memory used, including the call stack in recursive algorithms or auxiliary data structures. Both are critical for determining the scalability of your solution. The provided Python code is a placeholder for LeetCode problem number 1113, which is currently unavailable. The code defines a class solution with a method solve that takes an input parameter input_data. The method contains placeholder logic that directly returns the input data. This structure adheres to the typical LeetCode format, where solutions are implemented within a class named solution and specific methods are designed to solve the problem at hand. Once the problem details are known, the placeholder logic can be replaced with the actual implementation tailored to the problem's requirements. This is the Java implementation of the problem. The logic mirrors the Python solution structure, using Java's class-based approach and type declarations. The method solve takes object as input and returns an object to allow flexibility due to the lack of specific problem details. To begin, we are looking at a basic input case where the input data is a list containing the numbers 1, 2, 3, and 4. The placeholder solve function initializes by receiving this input, and at this point, the state simply reflects the input data as 1, 2, 3, 4. Next, the function applies its placeholder logic, which is a straightforward return of the input without any modifications. As a result, the state of the output is also 1, 2, 3, 4. Finally, the function produces this output list, 1, 2, 3, 4, as the result of the computation. Now, let's explore an edge case where the input is an empty list. The placeholder solve function begins by receiving this input, and the state at initialization reflects this as input_data equals. The placeholder logic then directly returns the empty list as the output, without performing any additional operations. Consequently, the state of the output is also. The function concludes by outputting an empty list, which matches the input in this case. In the third example, we examine the case of a large input where the data consists of a list of integers ranging from 0 to 999. The solve function begins by initializing with this input, and the state at this point is represented as input_data equals 0, 1, 2, 999. Following the same placeholder logic as before, the function directly returns the input list without making any changes. As a result, the state of the output is identical to the input, represented as output equals 0, 1, 2, 999. Finally, the function outputs the complete list of integers from 0 to 999, represented as 0, 1, 2, 999. This demonstrates that the placeholder logic consistently returns the input data as is, regardless of whether the input is small, empty, or large in size. In this implementation, we are analyzing the time complexity of the provided function. The function, as described, takes an input called input_data and directly returns it without performing any additional operations, such as loops, recursive calls, or complex computations. Since this is the case, the time it takes to execute the function does not depend on the size of the input. Whether the input has one element or a million, the function will always perform the same single operation, returning the input. This behavior corresponds to a time complexity of O(1), also known as constant time, because the function's runtime remains fixed regardless of the input size. When evaluating the space complexity, we consider both the auxiliary space used by the function and the memory required to store the input. In this case, the function does not create any new data structures or temporary variables beyond the input parameter, input_data. This means the auxiliary space usage is O(1), or constant space. However, we must also account for the input itself. If the input size is n, then the memory required to store the input is proportional to n, leading to a space complexity of O(n). So, while the function itself uses minimal additional memory, the overall space complexity is determined by the size of the input, which is O(n). Now, let's compare the placeholder implementation to a hypothetical brute force approach. Typically, brute force solutions involve iterating through the input, performing calculations, or applying operations that significantly increase computational cost. For example, brute force methods often result in time complexities like O(n) or O(n squared, depending on the operations involved. In contrast, the placeholder implementation is computationally efficient, as it performs no operations on the input. This results in an optimal time complexity of O(1). Additionally, the best, average, and worst-case scenarios all yield the same time complexity of O(1), since the function's behavior does not change based on the input size or contents. This consistency highlights the simplicity and efficiency of the implementation. Finally, let's solidify our understanding with a mathematical proof. For time complexity, the function performs a single operation, returning the input. Regardless of the input size, the number of operations remains constant at 1. This confirms that the time complexity is O(1). For space complexity, the function itself uses no additional memory beyond the input, meaning the auxiliary space is O(1). However, the total space complexity must include the memory required to store the input, which is proportional to the input size n. Therefore, the space complexity is O(n). This concise breakdown further reinforces the efficiency of the implementation in both time and space usage. In this section, let's talk about some common mistakes candidates make when solving problems and how to avoid them. One of the most frequent errors is misinterpreting the problem statement. This happens when candidates overlook key requirements or constraints, leading to solutions that don't align with what the problem is asking for. For instance, if the problem involves arrays, it's important to confirm details like whether the array is sorted, whether duplicates are allowed, or if there are size constraints. Next, we have inefficient solutions. Jumping straight to a brute force approach without considering efficiency can lead to time limit exceeded errors, especially for large inputs. To address this, analyze the problem's constraints carefully and aim for the best possible time complexity. For example, if an O(n log n) solution is achievable, don't settle for O(n superscript 2). Another common issue is neglecting edge cases. Forgetting to test for scenarios like empty arrays, single element inputs, or maximum constraints often leads to runtime errors. For example, if the input is an array, you should always test edge cases like an empty array, an array with just one element, or very large arrays with lengths up to 10 to the power of 5. Finally, choosing the wrong data structure can complicate the problem unnecessarily or reduce performance. For example, using a list for lookups instead of a set can increase the time complexity from O(1) to O(n). Always consider the strengths and weaknesses of the data structures you choose. Off by one errors are another common pitfall, especially in problems involving indices, loops, or ranges. These errors typically occur when boundaries aren't handled correctly. To avoid them, double-check the conditions for variables like I and j in your loops to ensure they align with the problem's requirements. Now, let's move on to some interview-specific insights. First, recognizing patterns is key. Many problems are variations of common techniques like sliding window, two-pointer, or divide and conquer. Identifying these patterns early can save you valuable time. Also, optimize your solution as soon as possible. Interviewers often appreciate efficiency, so once you have a brute force solution, take a moment to discuss its limitations and propose optimizations. Clear communication is another critical factor. Talk through your thought process, including how you plan to handle edge cases, why you've chosen specific data structures, and the trade-offs involved in your approach. Finally, manage your time wisely during the interview. A good rule of thumb is to spend about 5 to 10 minutes planning, 25 to 30 minutes coding, and the remaining time testing and refining your solution. Let's explore some related problems that share similar concepts or techniques. For example, the two-sum problem, which is LeetCode number 1, relies on efficiently finding pairs, often using hash maps for optimal performance. Another example is the longest substring without repeating characters, LeetCode number 3, which uses the sliding window technique to identify substrings with unique characters. Merge intervals, LeetCode number 56, focuses on sorting and merging overlapping ranges, while binary tree-level order traversal, LeetCode number 102, emphasizes breadth-first search for traversing tree structures. Now, in terms of alternative approaches, you can always start with brute force. This method is simple and straightforward, making it useful for validating correctness, but it's often inefficient for large inputs. The trade-off here is ease of implementation versus poor performance. On the other hand, optimized approaches like sorting, binary search, or dynamic programming provide better performance but are more complex and require a deeper understanding of the problem. Hash maps or sets can also be incredibly helpful for problems involving lookups, duplicate handling, or frequency counts. While these structures use extra space, they significantly improve time complexity and are often worth the trade-off. Another valuable technique is divide and conquer, which involves breaking the problem into smaller subproblems that are easier to solve. This method is particularly effective for problems like merge sort or binary search. However, it's important to consider the trade-offs. While divide and conquer can lead to elegant and efficient solutions, it often involves recursion, which can introduce overhead and potentially lead to Stack Overflow issues if not implemented carefully. Understanding when and how to apply this technique is key to leveraging its strengths while mitigating its drawbacks. Thank you for following along. In this session, we provided a structured framework for solving coding problems when details are missing or unclear. Remember to break problems down into smaller steps, focus on edge cases, and optimize where possible. Keep practicing, and you'll continue to improve your problem-solving skills. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!